Here we come to the last sections in the chapter 9 here. Here is talk about the how do we use the superposition principle to solve for the indeterminate problems. And the concept is pretty straightforward, and however, I would suggest students to, after completing these sections, and you should take more kind of examples to exercise to polish the skills we talk about here. Okay, so let's talk about the how do we apply the superposition principle. So here we come up with is one example, and on the left hand side, that is the example we've seen in the previous sections. And from here you can see there's a more the necessary support. There's a more support than necessary to make the whole thing in static equilibrium. Okay. So from here, the left hand side here, that is the anatomy of the loading, including the given loadings, and that is this one here. Okay. And then this distributed loading can be in statics can be equivalent to the single point loading. Okay, so and that single loading, basically this kind of equivalency can be seen in your learning of statics. And here let me skip off the detail. On the other side, in terms of reactions, we have the bending moment at the clamp side, first one, and we have reaction force, vertical and horizontal at the clamp side, and also at support B here we have these things. So from here you can see the numbers of the unknown reaction. Here we have MA, and this one we have the AX, and we have the AY, and we have the reaction force B here. The number of equilibrium equations is this one. The force equilibrium in the horizontal direction is equal to 0, and in y direction equal to 0, and the bending moment at any point equal to 0. So here we have 4 unknowns, 3 equations, and then here is the, apparently that is the static indeterminate problem here. So here so here we're going to look at how do we apply the superposition principles. And the way we can try is this. You pick one support. Okay, you pick. So for this problem, we have one additional unknowns than the number of the static equilibrium equations. So let me pick using different color. So in this way, let me pick this one. This one is the additional. Okay, that is one additional than the 3 equilibrium equations. So I dedicate to this one. So for this reaction, that is regarding the support here. Okay, so that is our focus. We pick this support and replace the support. So here I'm talking about is the procedures. Procedures of apply the superposition to indeterminate problem. Okay, so we pick a support. Okay, for example, here I pick support at B, and replacing the support by a reaction. Okay, so replace the support, which means replace the constraint. Okay, the support here is a constraint, so that a constraint preventing the vertical displacement. Replace the constraint by its unknown reaction. Okay, and here is RB. Okay, so that's step 1. And step 2, step 1 the first point, and step 1 the second point is this. Also recognize the support here, that is the constraint preventing vertical displacement. So that means we impose the yb equal to 0, because this one is due to the constraint of the support here. The support B here is simply supported, and that prevents any vertical displacement. So this is the one we observe from such a constraint here. Okay, so the 2 points in step 1 basically coming right into here. So now step 2. Step 2 is to recognize this equivalent description of the original problem by decomposing this system into the summation of the loadings. So one is from distributed loading omega. The second one is due to the loading that is from reaction here. Okay, so that's step 2. You decompose. You decompose the systems, and in terms of the loading, in terms of the load, for each type of the load you decompose into one subsystem, and here we have in total 2 kinds of the load. So here 2 kinds of system. Step 3. Step 3, and in particular we focusing on, for each subsystem we focus on what's going on deflection at the B. B is where the support we picked. Okay, so step 3, you calculate the corresponding displacement for individual systems, for example YB, and for this subsystem 1, and that is this one, and for this one is YB, and that is due to R here. Okay, this YB is downward, and so let me say for example the sign convention. So step 3, let me take the sign convention positive. Positive sign convention downward. So for this case, this is positive, and this is upward, this is negative. Okay, so positive minus, and this one here, apply the superposition principle. Basically with the sign convention, the summations of the diffraction at point B must be equal to 0 here. Okay, so step 3 basically is to implement this one. Step 3 is to apply the superposition principle. Use summations, you take summation of the situations, and then have the diffraction at B here equal to 0. So that is the 3 steps, and in detail we can look at individually here. So again, the first one, we decompose into the subsystems like the showing here. Okay, and then here is the detail. Replace the support B by reaction RB here, and then recognizing this one. Okay, then you decompose, you use superposition principle to decompose 2 subsystems here. Okay, and then set the YB of figure A equal to 0. So basically using the superposition principle to like this one. So basically that is our previous step. In the previous slides, that is step 1, this is step 2, and that is step 3. Okay, and again that refer to our previous slides, and that's a step 1, 2, 3. So look at into details, and before the details, I'd like to introduce the use of the appendix D. And assuming right now you know how to calculate, how to determine the equation for the diffraction of the beam under, for example here we listed is seven cases. The 7 cases are very common. So that is a typical example. We tabulate the result, and here I assume you know how to calculate the diffractions, equation diffraction for each case like this one, and that is what we exercise in the previous sections here. So here we directly utilize the tables. Okay, for example in this column, the basically showing is here is the magnitude of the diffraction and this one is the y maximum. Okay, here I explain how to utilize the table, and here this is a minus sign. Okay, so here if you look at this carefully, it's a minus sign. Minus sign simply indicating that is the downward. Okay, so basically in the diffraction here, the minus sign indicating is a downward. That's a sign convention. And the slope at the end, so basically the slope at the end that has the magnitude equal to that much. Okay, so basically that indicating that is slope. Sorry, let me put the drawing in a better way. If you would take a tangent, and tangent, so this is the endpoint. If you would take the tangent to there, so this one is a slope at the end. Okay, slope at the end. The magnitude equal to this. Okay, the magnitude equal to this. And let me erase this one. Then here, there's a minus here. If you look at this carefully, there's a minus. So the minus sign indicating the slope is in clockwise direction. So here, this is slope. Okay, inclinations of the slope from the horizontal is rotated clockwise. So that's a sign convention. So this sign convention for slope, that means clockwise. Okay, so here we proceed for the second case. For the second case, that is distributed loading on the cantilever beam. So this is a magnitude. Okay, so this is a magnitude, and minus indicating is downward. Okay, so this is a magnitude of the slope, and the minus indicating that is the clockwise kind of inclinations here. Okay, so the same thing for beam, cantilever beam under the bending at the free end, that is the magnitude with the direction that is downward, magnitude, and direction clockwise. Okay, in the similar way. So now we look at say for this case, for case 5 here. For case 5 here, and from earlier the analysis, we have to describe the diffraction into two pieces. Basically, in the left hand side, the segment between 0 and A. Then the second one is we have the description between the segment from 0 to from A to B, from the middle, from this point to B here. Okay. So for this tabulate result is listed two values, and one theta A. Theta A is the slope at A here. So let me say A is here. If you draw the tangent line, so this is the slope here, and this slope is given by this one. Again, this is the minus sign. Minus sign, that means the inclination of the slope is rotated clockwise. A theta B, so that is a theta B here. You draw a tangent, so this is a slope, the magnitude equal to this. Okay, and the positive sign, that means the inclinations of the slope is rotated counterclockwise. So hopefully you know the whole situations. So let me do this one here. So for slope, so here the minus sign, that means the slope is in these orientations. Okay, the positive sign is, let me do in this better way. So if this is the this is a horizontal line, okay, then the positive slope is they are rotated counterclockwise. Okay, the negative slope is the rotate clockwise. Okay, so that's a positive negative one. Okay, so keep those things in mind, then we can apply the table here to solve these questions here. Okay, see. Okay, so for this example here, so for this example here, we have the this one is definitely is in statically indeterminate problem here. So here I choose to replace this constraint by a reaction force. And again, step 1, choose this support and replace it by reaction force RB, which is unknown, and also imposing the diffraction equal to 0, because here that is the support here simply supported the vertical diffraction equal to 0. Okay, so now we have redescribed the problem in terms of the loading and like this one. So right now we recognize we have this distributed loading, and so we decompose into a subcase like this. Also we have upon loading, then we have the subcase like this one. So here we simply applying the step 2 superposition principle applied to here. Okay, so under this case, I'm going to solve for the problem. So here this is the per hour procedure. This is step 1, and step 1 basically come to this kind of the descriptions. The step 2 apply the superposition principle to come up with such a description here. Okay, then step 3, I'm going to apply the appendix D table to solve for the problem here. So right now again we have subsystem 1, so let me call this subsystem 1 and this is subsystem 2. I'm going to apply the tables, the appendix D, individually to each of the subsystem. So this is the first subsystem, and here we can pick up that is the case 6 from the appendix D. Okay, so from here what I need is the first one. I need to know what is this number here. Okay, so for that number I simply plug in, and so for this case this indicating x equal to 2L/3, so I printed this is a y/x. Okay, so this is the y/x. So I use these equations with x equal to 2L/3. Okay, so plug in, then I have this number here, and again the minus sign indicating that is a downward. Okay, so keep this number in mind. Then the second subsystem is this one, so we adopt the case 5. For case 5, that is they give us the pattern of the diffraction equal to this number, and this number is negative for downward, but here we have a force pointing upward, so we pick the same pattern, but we need to change the sign here. Okay, so for this case we simply yeah, you can pick this pattern here. Okay, and then you simply plug in the whole things, and that is a result like this one. Okay, you can double check, and or otherwise you can try to use these equations. You can use this equation here. You can use this equation. This is a y/x, or you can use this equation using y/x and with x equal to 2L/3, and in this equation we have b, and b equal to L/3, and this is a. Okay, so this is the a equivalent to our problem, the pattern here. This is b. Okay, so b equal to 3. So also you can use this equation. You can proceed the calculation, and that is the result here. Okay, so for this case, that is the magnitude, and with a positive sign, that means this is upward. Okay, so right now earlier we have found, applying the tables individually, we found this number downward, we have this number upward, and here we apply the superposition principle. So that means at point B, the superpose each of the subsystems that is equal to this one, and when we superpose that is equivalent to the original problem, there the diffraction at B equal to 0. Okay, so here in this statement we have applied the superposition principle here. Okay, so from this case, single equation, and here how many unknowns? We only have one unknown. You can solve for RB. Okay, so that is the end of the step 3. And the remaining additional problem is this. For this problem, we also like to for the deflected system, we like to find out what is the slope at A. Okay, so that is the additional problems for this one. So we say how much we can do about this one. So basically here we want to know what is the slope. So this is the slope. Let me use theta A equal to how much. Okay, so that simpler concept is this. We use superposition principle. So this is called the theta A and W. Okay, so something like this one here already. And this is in the similar way. So this is a slope, and using this signal, okay, and using this symbol. So theta A of the original one, again, here is the superposition principle, equal to theta A, this number, plus this number. Okay, so as long as we have the description for this one, then we can find out the result. So the remaining slides is to answer what is this and what is this. Okay, so for this case, and we remember, and here I highlight again, for the distributed loading, we have case 6, and for the point loading, we use case 5, and right now we focus on our slope here. And for the slope at point A here, we have this pattern. We have this pattern, and positive, basically positive is for one end, positive is for this end, and negative is for this end. Okay, so basically for this end we have the pattern here. So this pattern is, using the pattern is negative, and omega L3, I simply right now I copy this one, and 24 EI. Okay, so right now we look at this case, and this is omega, and this is omega, and the whole thing is L. So basically we can directly copy the information here. Okay, so that is this number here. And for this number, right now I'm going to determine this one for RA, and simply theta A, I simply pick out this pattern here. Okay, so theta A, let me copy that one. So directly copy. Is this one, so minus PB L square minus B square, and then 6 EIL. Okay, now I'm going to do the replacement of the parameter here. So compared to this case, this is a formula based upon this pattern. This pattern with the segment length A and B compared to our problem statement here is the two numbers. So basically compared to the number, the parameter to parameter, so here you can see B must be replaced by L over 3. Okay, and the whole length equal to L, and that is the same as this one, so that is the same thing. So keep those things in mind. And oh, one more thing here, one more thing I forgot. So let me erase the unnecessary information here. So probably if you have identified, you can say for the patterns, the P is downward, so that means producing the slope at A is negative. Okay, so that negative is due to this shape, and that is P downward. However, for this case, the loading is upward, so when we apply this pattern, this one producing a positive slope. So here, I think here we have to change it into the sign. Okay, so that is the last one that I come up with. We need to pay attention. And again, when we apply the patterns from the appendix, you need to do the adjust accordingly. For example, here the loading is upward and loading is negative. You need to change the sign here. Okay, so that is what we've done before, and this is the one like we listed. And then this one, here from here this is negative copy from our appendix, and this negative from up here, the negative disappear because here due to the sign. So I think the better way is we right away we put up the positive sign here. Okay, so anyhow, so that is the number here. So we simply add it up together. Okay, so add it up together eventually give our sign is negative. So that means the eventually for the our the superposed system, this is the still the slope is inclined clockwise like this shown here. The magnitude is equal to this number. Okay. So this is the last example here. So we want to determine the reactions at B and also reaction at E. Okay, we want to determine reaction at the two supports here. So basically this problem you can try to apply. How can we see it? So here I'm going to take the free body diagram on the beam DE and beam AB. Okay, the two beams are used in this configuration to support a loading P here. So basically here you can see at the contact between the two beams, and as I highlight here, and that's an action reaction. Okay, so basically at the contact of the two beams, and I know this is the action reaction force. Okay, RC is a reaction, and right now it's unknown. We don't know the value. I want to solve for this value first, and then before we can answer the action, the question, what is the reaction at the support B and E there. Okay. So we have done this one, and we have to apply the superposition principle to each of the case. Then we can see what happened here. So in this case, for AB, this is A, this is B, and AB is simply supported. So let me draw this one here, simply supported, and it is under the RC. Okay, directions, and deflected shape will be something like this one here. So, and then also we can see the portions, the beam CD, and CD that is again simply supported. So simply supported. And then for here C, we copy the force here. This is RC. Okay, and then also the loading is P here. Okay, so basically this one is the CD is equivalent to the loading is P minus RC. Okay, so under this case the deformed beam would be something like this. Okay, so let me call this is the deflection here. Let me call the Y at point C, and that is the due to, let me call this is the subsystem 1. Okay, and again this is the diffractions at point C, and let me call this is a subsystem 2. And from the original problem statement you can see if the both of the beam not fractured, not broken, then the deflection at point C must be consistent. So which means the YC from this case must be the YC from this case. Okay, so this is called the compatibility equations. But anyhow, this is an observation from here. Assume the both beams are not fractured, not broken, then they must have the continuous this the kind of description here. Okay, so here let me write it up clearly. So that means YC due to subsystem 1, that is this number here, equal to this number here. Okay, So now from here and down the remaining is to answer what is YC1. YC1 basically here you see I highlight we adopt the appendix D case 4 here, and we use this pattern here. For these patterns, basically you can replace the for this case using this generic formula here, and the YC basically equal to P. P here is RC. Okay, I simply pick up this pattern here, and the magnitude is 3 and then 48 EI. Okay, and this one again, this YC downward, so diffraction is downward. And what is YC2? YC2 here, that is again adopt this pattern here. The loading right now, this one, oops, this is the magnitude of the load here. Okay, compared to this one, the magnitude of the load is P minus RC. Okay, and multiply with L cube and divide by 48 EI. And again, this loading is downward, so that is YC2. So basically the two number must be equal. The two number must be equal, then you can solve for RC. So once RC is solved, then basically the remaining from here you can see from here due to the equilibrium, and you can shoot right away to see the reaction at RB should be equal to RC divided by 2, and then reaction at A should be RC equal divided by 2. Okay, so for this case, the reaction at RD should be equal to P minus RC divided by 2, the same thing here. Okay, so this is the detailed calculation.